Hello! In this video, we are going to look at the following problem. Suppose we kick a ball into the air at initial velocity v0 in acceleration due to gravity g. And let's assume that we kick our ball above a hill that's angled downward at angle phi. Given those three things, what is the launch angle that we kick the ball at so that we get the maximum distance traveled? Okay, so let's establish some coordinate axes for this problem. Let's say that this is the x-axis, and this is the y-axis. So, our ball is starting at the origin. And let's say that when we kick our ball into the air at some launch angle theta, the position at which the ball strikes the hill we'll call p comma q. And so what you have to notice here is that when we kick the ball, or maybe throw the ball into the air, the launch angle can vary between negative phi and 90 degrees. So then, what happens to the position at which the ball strikes the hill as we vary the launch angle? Now notice that as we vary the launch angle that we kick the ball at, the distance that the ball travels changes as well. And so our goal is to figure out the launch angle that we kick the ball at such that the ball travels the maximum distance. It turns out that that path will be given by this orange path, right? This orange path is the path that we could kick the ball through such that we get the maximum distance traveled, right? This right here is the maximum possible distance we could kick the ball. And so our goal, essentially, is to figure out the launch angle of this orange path. And so, yeah, that's pretty much the idea. And so what we're going to think about is how changing the launch angle causes the horizontal displacement p to change. As we saw, when the launch angle was essentially negative phi, p was essentially 0. And same thing for when the launch angle was essentially 90 degrees, p was essentially 0. But as we increased the launch angle from negative phi to 90 degrees, we saw that p increased and then decreased. So this right here is where we have a maximum distance traveled. And we'll say that this maximum distance traveled occurs at launch angle theta m. And we want to find what theta m is. And also I should say that the p-value corresponding to this we could call pn. So then, how do we find what this launch angle is? Well, notice that because this is a maximum, we have a horizontal tangent line here. If you recall, a horizontal tangent line is another way of saying that the derivative of p with respect to theta equals 0. So another way of looking at this problem is we want to find theta when dp over d theta equals 0. Okay, so how do we do that? Well, we're going to need an equation consisting of all 5 of these things. And so how do we get an equation like that? Well, we can consider the motion of the ball. We have the horizontal motion of the ball and the vertical motion of the ball. As for the horizontal motion, we know that horizontally we have constant velocity. Therefore, displacement equals velocity times time. The horizontal displacement of the ball is p. Now, the horizontal velocity of the ball is a constant. So to get the horizontal velocity of the ball, all we really need is the initial horizontal velocity of the ball, which is really just v0 cosine theta. And simplifying this, we get, so that's the horizontal motion. Now let's talk about the vertical motion. As for the vertical motion, vertically, we have constant acceleration, which means we could use one of our kinematics equations. Which kinematics equation do we want to use? We want to use the one that doesn't contain final velocity, because we don't know anything about the velocity at our final position. If you recall, the kinematics equation that doesn't contain final velocity is this one. Now, the vertical displacement of our ball is q. Now, Vy naught is our initial vertical velocity, which is really just V naught sine theta. As for our vertical acceleration, that's really just the acceleration due to gravity. But notice the acceleration is pointing downward, which means the acceleration is negative. G is positive, 9.8 meters per second squared. And therefore, to get the correct sign for the acceleration, we need to put a negative sign in front of G. So really, the vertical acceleration is negative G. Simplifying this, we get this. So we have two equations. We want one equation, right? We want a single equation consisting of all five of these things. So what we should do is we should combine these two equations into one equation. And we can do that by eliminating time, right? Because we don't need time in our final equation. And so to combine these two equations together, what I'm first going to do is I'm going to solve for time in this equation. And that's what we get. And now we'll just plug this in to the other equation. Okay, so now let's simplify this down. Notice the V naughts cancel out. And sine over cosine, if you recall, is tangent. Now I'm going to write this as a single fraction. Notice in the numerator we have gp squared. In the denominator we have 2 V naught squared cosine squared theta. So now we have combined these two equations into a single equation. But remember, we want our equation to consist of all five of these things. And we shouldn't have anything else, right? But notice, we have Q in our equation. Q is not one of these five things. So we're going to want to re-express Q in terms of these five things. Well, luckily, we have the ability to do that. Notice, from these 2 points, we can construct a right triangle. Right, and notice the side lengths of the right triangle just correspond to the horizontal and vertical displacements of the ball. So really, this side length is the horizontal displacement, P. This side length is the vertical displacement, Q. But you have to be careful because it's actually negative Q. The reason why is because Q is negative, right? This point is below the x-axis, so the y-coordinate must be negative. Q is negative, but every side length of a triangle is positive. So that is why we have the negative sign in front of Q, to assure us that the side length is positive. Now another thing is that the x-axis is parallel to this side length. So really, these two angles are alternate interior angles, so they must be equal. Okay, so now we see that the tangent of phi is equal to negative Q over P. And if we solve for Q, we get Q equals negative P tangent phi. So now we have Q in terms of these five things. So now we're going to replace Q with this. Okay, so now notice all three terms contain P in it. So I can divide P on both sides to eliminate them. Right, but the P squared is just going to become P. And therefore, our equation becomes now it turns out that it's going to be useful later on if I re-express this term in a slightly different fashion. So notice we have G over 2 V naught squared, and then we have P, and then we have 1 over cosine squared theta, which is really just secant squared theta. And so now notice we have the equation that we want. We have an equation consisting of all five of these things and nothing else. So this is good. Now let's move back up to the top. Okay, so the reason why I wrote it out twice is because it turns out this equation is also going to be important later on, right? That was good. So I've kept it up here for safekeeping. But now that we have an equation consisting of all five of these things, we are ready to bring dp over d theta into the picture. To do that, what we could do is we could differentiate both sides with respect to theta. Okay, so this is where we really need to think about what are our variables and what are our constants, right? These are our constants. So starting with the left-hand side, phi is a constant. So really, we're taking the derivative of a constant, which means the derivative of this is just 0. Right-hand side is a little bit more complicated, right? We have the derivative of this minus the derivative of this. Well, the derivative of tangent, if you recall, is just secant squared. And let me be as clear as possible. I'm going to subtract the derivative of this. Now, first of all, notice that g over 2v0 squared is a constant because g and v0 are constants. Therefore, we can pull this outside of the derivative. So this is really the derivative we have to evaluate. Notice p is a function of theta, right? The horizontal displacement p depends on the launch angle which we throw the ball at. So p is a function of theta, secant squared theta is a function of theta. So really, we're taking the derivative of two functions of theta multiplied together, which means we're going to need to use the product rule. If you recall, the product rule looks like the following. So let's use the product rule. The way I like to do the product rule is I think of it as derivative, no derivative, plus no derivative, derivative. So starting with derivative, no derivative, we have dp over d theta secant squared theta plus no derivative, derivative. So then that means we're going to be doing p times the derivative of secant squared theta. Now that's a little bit of a difficult derivative, so let me write that off to the side. To evaluate this derivative, we need to use the chain rule. If you recall, the derivative of something squared is 2 times that something. But then the chain rule says that we have to multiply that by the derivative of secant theta. If you recall, the derivative of secant is secant tangent. And so, simplifying this, we get this. So really, p is multiplied by this. Okay, so this is what we get after differentiating both sides with respect to theta. Notice, all three terms contain secant squared. So we can divide secant squared theta on both sides to get rid of them. And what we're left with is this. Now, really, our goal is to find theta when dp over d theta equals 0. So now it's a good time that we set dp over d theta equal to 0. And so after setting dp over d theta equal to 0, we have this. Now, remember, when dp over d theta is equal to 0, that is where we expect our maximum displacement to occur. So really, I'm going to call p Pn. And I'm going to call the launch angle theta that corresponds to Pn theta n. Right? Our whole goal is to find the launch angle theta n. Right? Now notice 2's cancel out. So really, we've set dp over d theta equal to 0. What we want to do now is just figure out what theta m is, right? That's what we want to find. But does that mean that we should just algebraically solve for theta m in this equation and call that our answer? Well, no, because if we algebraically solve for theta m in this equation, we're going to have theta m in terms of Pm. We want theta m in terms of only these three things. Therefore, just this equation is not enough to obtain theta m in terms of these three quantities. But luckily, we have another equation, right? So really, it looks like the best way to go about this is to algebraically solve for Pm in this equation and plug that into the other equation, and then algebraically solve for theta m. So that's what we're going to do. Let's algebraically solve for Pm in this equation first. If we add this to the left-hand side, we get Next, I'll move these two to the other side by multiplying both sides by v0 squared over g. So those go away. And so we're left with, oh wait, I forgot theta m, my bad. And then dividing tangent theta m to the other side, we get, but really 1 over tangent, if you recall, is just cotangent. So we have algebraically solved for Pn. So now let's move back up to the top. Now really what I want to do here is I want to plug this in for P into this equation. But before we do that, I think it's important to note that this equation relates the launch angle that we kick the ball at to the horizontal displacement P for any launch angle that we kick the ball at. In our case, we're interested in the launch angle theta m. So I'm going to be replacing theta with theta m, and the horizontal displacement that corresponds to that is Pm. So now we're going to replace Pm with what we have here. Now notice immediately that the v0 squareds cancel out and the g's cancel out. So really what we have here is this. Now really, our goal now is to algebraically solve for theta m. And this looks like a complicated equation because it turns out it's really nice if we re-express the right-hand side completely in terms of sine and cosine. If you recall, tangent is just sine over cosine. Cotangent is just cosine over sine. And secant squared is just 1 over cosine squared. Notice that cosine over cosine squared is just 1 over cosine. And so now I'm just going to rewrite this. We have this. Now we can combine these two fractions into a single fraction by getting a common denominator. Notice all we have to do is multiply both the numerator and denominator of this fraction by 2 sine theta m. And so from here we get, and so this is where we're at this point. But to some of you, it still looks a little complicated, but it turns out that the numerator and denominator are both trig identities that make this look way nicer. It turns out that the numerator is just negative cosine of 2 theta m, and the denominator is just sine of 2 theta m. And really, cosine over sine is just cotangent, so this is negative cotangent of 2 theta m. Notice we could divide negative 1 on both sides to get tangent of phi equals cotangent of 2 theta m. And so this is the equation we have now, which is a lot more simpler than what we started with, right? So now let's move back up to the top. So then how do we solve for theta m in this equation? Well, it turns out we can re-express cotangent in terms of tangent, right? It turns out we have the following trig identity. So really, this is just the tangent of 90 degrees minus 2 theta m. So this is what we have. Now, the tangent of this is equal to the tangent of that. Therefore, this must be equal to that. Except this isn't exactly correct because tangent has a period of 180 degrees. Therefore, this, we have to actually add 180 degrees n, where n is an integer. But it turns out, given the constraints of our particular problem, that is, the launch angle can only be between negative phi and 90 degrees. And the angle of the hill, phi, can actually only vary between 0 degrees and 90 degrees. Because of these constraints, it turns out that n must equal 0. If n is less than or equal to negative 1, we contradict these constraints. And if n is greater than or equal to 1, we also contradict these constraints. And I'll leave that as an exercise for the audience to verify that, because that's just going to take a lot more time. So because of these constraints, n must equal 0. and therefore phi must equal 90 degrees minus 2 theta m. So now this is really easy. We get 90 degrees divided by 2 is 45 degrees, and then we subtract phi over 2. So this is the launch angle that yields maximum displacement. And notice, because phi varies between 0 degrees and 90 degrees, theta m must vary between 0 degrees and 45 degrees. So the launch angle that yields maximum distance is in fact a positive launch angle. But another thing that's interesting about this is that this launch angle, theta m, does not depend on the speed at which we kick the ball at, nor does it depend on the acceleration due to gravity. It only depends on the angle of the hill. And so it's really interesting that we have that result. Now, there is one part I'm leaving out of this, and it's that all we have really found here is that this is theta when dp over d theta equals 0. We haven't mathematically shown that this value for theta yields a maximum value for p, right? We suspect it to be a maximum, right? So I leave it as an exercise for the audience. That was good. To verify that at this launch angle, p is in fact a maximum, right? So I leave that as an exercise for the audience. Let's go. I love doing that. All right, so yeah, that's pretty much it for this video.